everyone, I'm Ani, and my project is Astrotrack. Advances in the field of planetary science, particularly concerning our own solar system, have been dramatic over the last few decades. These advancements are largely due to developments in observing technology and more comprehensive astronomical surveys across the world. But with these copious amounts of new data comes a simultaneous need for more effective methods of analysis. Using more efficient analysis techniques, we can detect and characterize objects far more completely, and offer solutions that can extend beyond astronomy. Before setting out on this ambitious goal, I did some research to determine the extent of existing solutions to the problem. I found a Harvard paper that looks to utilize the Hopf transform, which is a line detection technique, in order to recover artifacts in astronomical images. But this is an image level effort rather than a catalog or database level effort. Another paper describes a novel streak detection technique to extract streaks from astronomical images. This also offers promise, but is in a very early stage of development, and it's still an image level effort. In addition to this, I discussed this problem with two of my research mentors at the University of Michigan, Professor David Gertis and postdoctoral researcher Ed Lin, who are both major contributors to deep survey analysis. After having these discussions, I sought out to quantitatively establish design constraints that I could use in my own model, which are detailed in my logbook, but in brief summary include the construction of light curves, the returning of object positions, a list of candidate matches, and doing so quickly and efficiently. I proposed three different approaches to algorithmically solve this problem using Python. The first design involves solving Kepler's equation, which is an equation that allows us to predict the position of these objects over time given their initial orbital elements. Then I use an online querying system to return a list of positional uncertainties for the candidate matches. The second design is similar, but uses a method of simulating the solar system, or n-body integration. This numerical technique allows us to get very accurate positions for these objects. The third and final design employs a combination of these two methods along with a novel technique of detecting the asteroids using the Hopf transform. This third design is the one I ended up choosing. It is a design that is shown over here, and a design whose mechanism has been shown in the video over here. Let's take a much closer look at the implementation of this design. Over 3 iterations. In the first iteration, the primary goal was simply to recover known asteroids and other minor planets using Kepler's equation, as mentioned before, then using n-body integration to predict the position of the candidate object far more accurately. The second iteration incorporates the use of Astroquery, which is a Python module that allows for calls to be made to JPL Horizon's ephemeris system. This is then used to return object ephemerides and positional uncertainties. The third and final iteration is also able to detect new objects by modeling the trajectories of objects over the night period as straight lines, then using the probabilistic Hopf line transform, which is a modified version of the standard Hopf transform. With this process, I recovered over 500 known objects and roughly 3 to 4 new objects for every known object, yielding a total of 3,000 objects in a single night of analysis. But we not only want to find these objects, we would also like to characterize them. And the best way to do this is by constructing a light curve. A light curve is a plot of the object's brightness over time. These can be analyzed to determine the period, size, and even the shape of some of these irregularly shaped objects. A few of the light curves are shown here, and period analysis using the Lomskargel periodogram is shown here. Of course, the design I implemented changed dramatically over the course of this project. As I mentioned, I utilized the probabilistic Hopf transform in favor of the standard Hopf transform for efficiency purposes. Also, I employed additional techniques to remove and denoise the data. This includes temporal sequencing and median filtering, the latter of which is a technique for image processing that has been adapted to this project. It is clear that the potential for this product is quite extensive. There are presently over 100 research institutions participating in the DES and deep surveys, and this number only grows every day. The project could be crowdsourced to thousands of amateur astronomers, allowing them to aid in research efforts in a method similar to present cryptocurrency mining. Executing this program on a multi-core computer could allow a whole night to be analyzed in less than 3 hours, a dramatic increase from current standards. The target audience for this project is clearly fellow researchers and astronomers who can now speed up their analyses and extend off of existing analysis. The line detection algorithm I mentioned has uses well beyond astrophotometry, useful in any kind of data science that employs sparsely scattered data that has linear trends in it. The social value of this project is quite apparent, as I seek not to make any sort of profit, but its open source nature allows researchers to collaborate easily on minor planet research. Other researchers can improve this project and adapt it to their own needs, but ultimately, the social value of this project, in my opinion, arises from its enabling of the understanding of our own solar system, and in this process allows us to make predictions about our own planet. Thank you for your time.